Well, hello everyone. If you hear me yelling at a cat, don't forgive me. He's just biting me right now. So maybe you just heard him. He's frisky. We're going to talk about acceleration this month, and we're going to start out with some definitions. Today we're going to go ahead and work or in this first part we're going to work on some graphs, and in the second part I'll go ahead and work on some examples. So we're talking about acceleration in this month's. Oops, that's supposed to say July, not June. Let me fix that right away. July. In this month's lesson, we're going to be working on acceleration, and we'll just start out with the definition. A lot of people actually mistake acceleration with velocity, so it's something you want to be a little bit careful about. Acceleration is actually how quickly velocity changes. I'll give you the second definition first. It's how rapidly the velocity increases or decreases, how rapidly it changes. So if you think about when you hit the accelerator on your car, that's the gas on your car, that's making you go faster. If you push down harder on it, it makes you go faster, faster. And if you hit it just kind of lightly, you'll speed up, but very slowly. But you're changing your velocity one way or the other. Actually, your brake is also an accelerator, but it's going to slow you down. It's going to change your velocity in a negative direction in a way. And we'll talk about that a little bit more. Because you can accelerate forward or accelerate backwards, acceleration is a vector. And the more technical definition of an acceleration is the change in velocity with respect to time. So this is going to be another slope, right? Change in velocity over change in time, which is what this next slide is talking about here. This is that definition that I just gave you, right? Um, average acceleration. Um, we There's also instantaneous acceleration. We can't really talk about that without calculus. Um, the calculus students, when you get that far, I'll even mention it in class, you're going to talk about tangent lines and their slopes. And we could actually estimate visually instantaneous accelerations, but we're not going to get to that in this lesson. Maybe we'll get to that in class in this fall when we do it. But we're going to talk about average acceleration. That little bar above the A just means average acceleration. I guess I should write that for you. So this is average acceleration. Let's see, acceleration. And that's acknowledging the fact that we don't exactly know what the acceleration was at any given time, but we do know what it was kind of overall. In the same way as like your average score for a class doesn't tell you what each individual assignment or test was, it just tells you how you did overall. So the average acceleration is, if you remember that delta symbol, that triangle, the delta symbol means change, so change in velocity over change in time. And the change in velocity is just your final velocity minus your initial velocity. Let me type that there a little nicer for you. That's final velocity minus initial velocity. But definitely you want to get used to that notation, the F and the I. And then delta t is just your change in time. Yeah, let me type that again. Change in time. And that you could actually call the final time minus the initial time if you want as well. So in this part, we're going to look at some visual examples. I got one down here for you. And that visual example talks about, well, it just shows you see a graph. The y dimension is actually x, which I know sounds strange, but that's your position measured in meters, and the x direction is your time measured in seconds. And I'm going to look at each one of these individually, so I'm going to look at the blue line first. If I look at the blue line, well, let's see what we know about this. If we look at the blue line, the position stays the same, the whole blue line. Well, that means whatever object this is isn't moving. So it actually means that the velocity of the blue line is 0 because this isn't moving at all. And in this case, because it is staying at a constant velocity of 0, the acceleration is also 0. That does not always mean that that your acceleration is 0 when your velocity is 0, though. in this case, it is because the velocity isn't changing. That's why the acceleration is 0, right? It's delta v over delta t. Well, if delta v is 0, we don't really care what delta t is. As long as it isn't 0, we're going to get 0 for the acceleration. So the fact that the numerator is 0 is why the acceleration is 0. There's actually many times when you have a velocity of 0, but the acceleration is not 0. And actually, if we talk about like a car, if you're talking about, hey, I'm at the stoplight, so my velocity is 0, but as soon as that light changes green, your velocity is still 0, but you hit the accelerator and your acceleration is not 0. So that would be an example of where your velocity is 0 and your acceleration is not. Or let's say you, I don't know why you would do this. Well, no, let's say you're parked in the garage and you need to back out of it. Well, as soon as you take it out of park, your velocity is still 0, but once you start backing up, your acceleration is not 0, and that would be a negative acceleration because you're going backwards. So just because your velocity is 0 doesn't mean your acceleration is. In this case, it is, but that's just kind of coincidence. I'm going to look at the black line next. Okay, if we look at the black line, we see that, well, the black line has this nice constant slope here. It's certainly going someplace. I could even say that it has a positive velocity. I don't know what value because I didn't put any scale on this, right? But if I did know, if I did have a scale, I could just say, I lost my marker. I could just say changing the x divided by changing the y, right? We did that in our last month assignment. And the acceleration, well, this is the velocity, if you look at it, is a nice even slope. So this is constant positive velocity. If this is a constant positive velocity, that means your velocity is not changing. So if we think of acceleration as change in velocity over change in time, I should say average acceleration, well, we have 0 over, I don't know what delta t is, but it's not 0, and that's going to be 0 again. Something I haven't talked to you about is what are the units, by the way, for acceleration. If we think about, okay, delta v over delta t, what are the units for that? Well, velocity is meters per second, and time is seconds. So that means we're dividing by seconds twice. Well, if we're dividing by seconds twice, that's like dividing by seconds squared. So your standard units for acceleration are going to be meters per second squared, and I should add that into both of these. It's kind of ugly units, meters per second squared. So that would be your units for your acceleration. Let's go look at our next lines. Let's do the red one next. Okay, if we look at our red line, now this one's a little bit more interesting. I see that this is going up, so certainly my velocity is positive, right? We have a positive velocity, but now I don't have this nice slope anymore. I actually have, if you look at this, this is almost like a parabola. This is when we're going up faster, we're going away faster. And because of that, that means my velocity is actually increasing. Okay, if my velocity is increasing, now that tells me my acceleration. That means my average acceleration, well, delta v, since my velocity is increasing, delta v is positive. And, well, delta t is still positive, if you will. It's just delta t. We're going to assume it's positive, which means we have a positive acceleration. And that's because this line, if you look at it, is getting steeper as we go out further. I might have mentioned this in Algebra 2 last year, but certainly the calculus students, you're going to talk about concave up and concave down graphs and how they affect minimums and maximums. And this would be a concave up graph. If you remember from geometry, concave up kind of has that bowl shape upward. And this red line has certainly an upward bowl shape, so a concave up. And that'll always have a positive acceleration if you're doing a position versus time graph. But you do, just like the last chapter, last section of June assignment, you do have to pay attention to what's on that y-axis. That caught some of you. In this case, it's position, but we're looking at the position increasing faster over time, which means we're accelerating in the positive direction. Now, if we look at the purple line, and I'm running out of room here, I'm going to scroll up and down a lot. But if we look at the purple line, it behaves in the opposite way. It's still increasing, all right? We still are going further away. X is always getting bigger. This looks almost logarithmic or something like that. So we're still, velocity is positive. But if we look at it, the velocity is, even though it's positive, even though we're going further away, we're going further away slower with time, which means the velocity is decreasing because the slope of this is going down. So the velocity is positive and decreasing, which is the opposite as the red, because the red was positive and increasing. As soon as we see we have a decreasing velocity, oh, that means when we're doing our average acceleration, we're going to have, so delta V over delta T. Well, if the velocity is decreasing, that means delta V is going to be negative. Well, a negative number over delta T. Well, that means we're going to have a negative acceleration. And again, I haven't put any numbers in, so we can't actually calculate it. But visually, I just wanted you to kind of get that idea. So the blue, steady, and the black, steady. So those have an acceleration of 0. The red is increasing with time, so that means that it's going to have a positive acceleration. The purple is concave down. It's decreasing with, the velocity is decreasing with time, even though the position is increasing. The velocity is increasing less quickly, so the velocity would be decreasing, which means we have a negative acceleration. All right, and one more graph for us to look at in this part, and then I'll create a second one later. So this says identify the acceleration for each region. Now we do have numbers. Also tell all information we can tell at 7 seconds. So let's look for each region first. So if I'm looking at 0 to 2 seconds, looking at that region, now we have velocity on the y-axis. So 0 to 2 seconds, well, my final velocity is 2 meters per second. And my initial velocity is 2 meters per second. And my time is 2 seconds, but that's just going to be 0 divided by 2, or 0 meters per second squared. So that would be for our first region. Our second region would be from 2 to 4 seconds. So 2 to 4 seconds. And if we look at that, our final velocity is, it looks like 3 meters per second. And our initial velocity is 2 meters per second. Again, over, it looks like a 2-second interval. Oops, that's messy. I don't know how that happened. That'll work. And, well, obviously that's 1 over 2, or 0.5 meters per second squared. I really should convert that to a decimal, but I'm not going to worry about it. If I look from 4 to 6 seconds, all right, again, I see it's a flat line, so I realize that the velocity isn't increasing or decreasing. If you just want to use common sense like that, you can just say the acceleration is 0. I'll actually write it out. The final velocity is 3 meters per second. The initial velocity is 3 meters per second. And the time is 2 seconds again. So that would be 0 meters per second squared again. And then our last region, from 6 to 8 seconds, okay, now this one has a pretty major velocity change. we're going from, our final velocity looks like -4 meters per second. I should put -4.0. Our initial velocity looks like it was 3 meters per second. And again, this time is 6 to 8 seconds would be 2 seconds, which would be -7.0 meters per second divided by 2 seconds, which would be -3.5 meters per second squared. And they ask us, what do we know? Tell all information that we know about time, 7 seconds. Well, if we look at this, if we look at the area under this part, that's 2 meters per second times 2 seconds, so that would be 4 meters that they went. Then for this part, we'd have an average, the average would be 2.5 meters per second. This is 2 times 2. This would be 2.5 times 2, which would be 5 meters. And then from here to here, I'm being messy now, this region we'd have 3 meters per second times 2 seconds would be 6 meters. And then, sorry, it's a mess. If we look at this region, we'd have an average of 1.5 meters per second times 1 second, which would be 1.5 meters. I know this is messy. 1.5, 6 would make 7.5, 5 would make 12.5, and 4 would make 16.5. So at t equals 7 seconds, the object moved, I forget what I said. What was it? 4 plus 5 plus 6 plus 1.5 equals 16.5 meters. The velocity is 0. I believe, right? Yep. Velocity at 7 seconds is 0. I need to extend. And the acceleration we just found was -3.5 meters per second squared. Sorry, the velocity is supposed to be 0 meters per second. That's messy. Let me rewrite that nicer. Is 0 meters per second, and acceleration is -3.5 meters per second squared. All right, I'm going to stop that part here so it doesn't